In this section, we're going to take a look at finding limits analytically.
First, we're going to start with a little disclaimer. In this section, we're going to take a look at some basic properties without any proof. We're going to state what certain simple properties of limits are. However, since we, in this section, do not have a formal definition of what a limit actually is, we're only going to take a look at the results of certain simple properties. In a calculus course, you then proceed to prove many of these properties, as well as take a look at and investigate thoroughly some more advanced properties. All right? So here we go. Our first property of a limit is, well, I suppose before we start naming them, let's give a simple sketch. Let's say you had a graph. Okay? Now, let's say I had a constant function, something like y equals to 5, y equals 12, y equals some constant. Okay? Here let's be specific. Let's say that's just the number 6. Okay? So now, let's say I wanted to take the limit as x approaches some number, and here I'll call that c. All right, so what is the limit as x approaches c of my function, which my function is just the constant y equals 6. Well, notice that if I cover up this point and say, okay, I don't know what happens at that point. Now, I do, but again, for the limit, you don't actually ever plug in the point. You don't ever actually say what happens at c. You say what happens as you get closer to c. Well, notice that in this situation, this is a constant. Even if this point wasn't there, I would still have the pattern that every other point for every other value of x always has a value of 6 for y. So what that means is, it doesn't matter what point I'm trying to plug in, because this is a constant function, I would expect that any point would have a y value of 6. So even if this wasn't here, even if this had a hole in there, I would still be able to take the limit by saying, oh, as I'm approaching from the left or from the right, my y values are always 6. So here the limit of this is equal to 6. Now you might say, okay, well that's a constant function, and if it's always 6, well then that means that your answer is always 6. Okay, no problem. But the same thing will be true for many simple functions. In fact, let's take a look at just the next simplest function. The next simplest function after a constant function would be something that's linear. For example, something like this. Let's just say that's something like y equals 2x, the simplest linear equation. And let's say I had a value of c. Well, again, the same thing would happen. Even if I had a hole right here, even if I covered this up, even if I didn't know what was there, if that was a secret, well, I could still tell from the path around here that as I approach x equals to c, then my y value is also approaching c, because remember, x and y are equal to each other at every point here. So this would be 0, 0, 1, 1, 2, 2, 3, 3. And on this side, if you're coming in from the left, you would say 5, 5, 4, 4, 3, 3, and so forth. So even if this point wasn't there, or if we didn't know what was there, we could still consider the limit as you approach. Notice that since y and x are always equal to each other, when x is equal to c, you would expect, and from here from the graph you can confirm, that from both sides you're approaching y equals to c. So if you take the limit as x approaches c of x, well, you just get c again. After all, that's your function. Yeah? So these begin our first two properties. So let's see here. Let's let c be just some real number in the domain of a function. So let oh, you know what? Let's use a instead of c, because c is used for a few other things in this section. So let's just call all of these a. It doesn't make any difference. It's just we're going to reserve c for other things. All right, so let a just be some real number. Then the following statements are going to be true. If you take the limit as x approaches a of some constant, you're just going to get the constant. Well, that makes sense. The whole function is always that same number. So as you approach this, well, so what? It's still going to stay that number because it's always going to be true. Here, y is always 6. So if you change your x value, so what? Your y is still going to be 6. The next property is, for this one here, you take the limit as x approaches a of x. Well, we saw that that's just a. All right, but let's keep going here. So here we have let a be a real number. All right, the next few properties are going to require us to have more than just one real number. So for our next few properties, let's say let a be a real number. And then we're going to take two other values, which we're going to call L and M. We're going to let those be real numbers as well. But not just any real numbers. They're going to be real numbers such that if you take the limit as x approaches a of some function, that's going to give you L, and the limit as you take a x approaches a of some other function, that's going to equal to M. So here, this L and this M are not just any numbers, they're the limits that you get when you take the limit of some functions. I guess I can actually even write that where f and g are functions. Where f and g are functions. Okay. So these are my conditions. This is what I need to be true in order for these properties to hold. So if I have these conditions satisfied, then the following statements are true. If I take the limit as x approaches a of a new function that I make by adding together the two old functions f and g, that's equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Or in other words, it's equal to L plus M. What this is saying is if you have the limit of a sum, that's the same as the sum of the limits. So I can either add together and then take a limit, or I can take limits and then add the answers together. And either way, I get the exact same result. All right, so that so here that's one property, that's another one. Here's a third property. The next property that we have is, oh, you know what? We're going to need one more number here. So let A and C be real numbers. There we go. Let A and C be real numbers. Any numbers is fine. Doesn't matter what they are. And here L and M are specifically the real numbers that are the limits of these two functions. All right. Then the next property is if I take the limit as x approaches a of a constant times my function, that's the same as saying I'm going to take the constant and multiply that by the limit as x approaches a of f of x. Or in other words, it's equal to L times C. So what this is saying is if I'm going to multiply this function by a constant, then I can either multiply by the constant first and then take a limit, or take a limit first and then multiply the constant. And it makes no difference, I'll get the same answer. When you take these two properties together, any operation, and a limit is a type of operation. It's like saying I'm taking a square root, or I'm adding, or I'm taking a logarithm. It is an operation. So here, any operation that has these two properties, where you can add either before or after you take the operation, and where you can multiply by a constant, either before or after, this is called linearity. So the limit is a linear operator. In calculus, that turns out to make things a lot nicer. It turns out that because of the linearity of the limit, because these two properties are true, because limits have linearity, there's going to be a lot of stuff that we can do easily and take for granted in calculus. If it wasn't for linearity, that would be a lot more difficult. Note here that where we say f of x plus g of x, note that it is possible for this to be a negative, so I suppose I should write this as plus or minus. So if I'm going to add two functions or subtract them, it doesn't make a difference. Plus or minus, and here that's plus or minus. So I can either add the two functions and take the limit, or subtract them and take the limit. And that's the same as if I took the limit and added, or took the limit and subtracted. So here this is plus or minus. I can either add or subtract. All right, so now my next properties, those two are, whenever an operation has both of those properties, that's called a linear operation. This is called linearity. The next ones are not linearity, but they're still true for the limit operation. If you take the limit as x approaches a of f of x times g of x, that's the same as if you took the limit as x approaches a of f of x times the limit as x approaches a of g of x. Or in other words, you can either multiply and take the limit, or first you can take the limit and then multiply. And either way, you get the exact same result. The fourth property, you at this point have probably guessed what the next one is, right? We have addition, subtraction, multiplication, division. And yes, it's true for division as well. If you take the limit as x approaches a of f of x over g of x, that's the same as if you take the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. So you can either divide and then take the limit, or you can take the limits and then divide those answers. So that's going to equal to L over M. And here there is one condition. You must make sure that your denominator is not 0, where M is not equal to 0. If M is equal to 0, then this is not defined in the first place. So it looks like the limit can be applied either before operations or after them. Addition, subtraction, multiplications, and divisions. Well, there are other operations. What about powers, like squaring and cubing? It works for those as well. So the limit operation can be thrown in basically whenever you want. You can either do all your arithmetic first and then throw in your limit, or you can take your limit one piece at a time and then do your arithmetic, or any mixture thereof. So the next property is if you take the limit as x approaches a of f of x raised to a power, let's see here, f of x raised to a power, which we'll call n. And you say, well, we haven't dealt with an n before. Well, that's going to be a little bit different. Here we have a specific requirement. Here that's going to be f of x to the power of n. That's going to be the same as if you take the limit as x approaches a of f of x first, and then take that whole thing raised to the power of n, which is going to be the limit L raised to the power of n. Here, the n has to be a counting number, 1, 2, 3, 4, 5, and so forth here, where n is a counting number. And finally, you notice that we have addition, subtraction, we have multiplication, division, we have a power, and, well, its counterpart would be the root, like a square root or a cube root, and it holds for that one as well. So if you take the limit as x approaches a of the nth root of f of x, whether it be square root, cube root, or whatever, it doesn't really matter. And that's going to be the same as if you took the nth root of the limit as x approaches a of f of x. Or in other words, it's equal to the nth root of L. And again, same thing here, where n is a counting number. So in all these other cases, the a's and the c's have been any real number, but here we want n specifically to be a counting number. 1, 2, 3, 4, 5, and so forth. All right. So this is a collection of properties that we have of limits. You take the limit of a function. All right. Now, we can put some of these together along with our first two simple ones, the ones that we saw in our graphs, and we get a third property that can be joined with these. That property is one of the nicer ones that we have, and it's because it applies to a function that we see all the time. All right. What happens if you take the limit as n approaches infinity? I'm getting ahead of myself. That's a calculus thing. What happens is the limit as x approaches a. Sorry about that. What happens when we take the limit as x approaches a of, and right here, this is one that we've already seen. What happens if you take the limit as x approaches a of x? Okay, well that's just a. Okay, but what happens if I take this and raise it to a power? Okay, so what is the limit as x approaches a of x to a power? Well, that's going to be, the limit as x approaches a of x, that whole thing raised to a power. After all, that was one of the properties that we saw over here. Whenever you have a power, you can either apply it to the function and then take the limit, or take the limit and then apply the power to the function. So here, I can apply the power to the function, or I can take the whole limit and then apply the power. Okay, well I know this limit is a, so this is a to the power of n. Okay, but what happens if I multiply that by a number? For example, let's say I take the limit as x approaches a of c times x to the n. Well, we have a property that says that if you're going to multiply whatever function by c, that's the same as taking the limit of the function and then multiplying by c at the end. Okay, so that's going to be c times the limit as x approaches a of x to the n, which is what? Well, we know that's a to the n because we saw that one in this line. So that's going to be c times a to the n. Like that. Oh, but what happens if I take several of these and add them together? So for example, let's say I take the limit as x approaches a of c times x to the n plus or minus dx to the power of m. Okay, so these are just numbers, and these are just counting numbers. All right, well, I have a property. In fact, that's the very first property we saw. That's linearity. Whenever we're taking the limit of a sum or a difference, we can take the limits first and then add and subtract. Okay, so that's going to be the limit as x approaches a of c times x to the n plus the limit as x approaches a of dx to the m. And here we see that that's just c. This x is being replaced by an a to the power of n. Okay, so that one's going to be ca to the n. But if we follow that same rule, notice the c and the power stayed the same, and just your variable got replaced by what you're approaching. Okay, so in that one, the power and the coefficient will stay the same, and only the variable will take the value of a. So here that's equal to cx to the n plus dx to the m. But what is this? Well, this is how polynomials are written. So what this tells us is that we can take the limit of a polynomial. I said it and I didn't do it. Here we go. That's supposed to have an a in there. So here, this is a polynomial. And notice we can take the limit as x approaches a of the polynomial. And what's the only difference between here and here? That's c x to the n plus or minus dx to the m. Oh, the only difference is these aren't x's anymore. They're a's. Oh, but the a's are what we were approaching. So what this does is it gives us a very nice property. It says that if you want to take the limit of a polynomial, you can just plug the number into the polynomial and that's your limit. So here's a property. Let f be not just any function, but a polynomial function. Let f be a polynomial function. Now you might say, well, that's nice. I can just plug in my number. Why don't I do that for other functions besides polynomials? We've seen before in previous sections that if you have certain functions, plugging in the number will give you something like 0 over 0, right? Something that's undefined. So that doesn't work for other kinds of functions, at least not necessarily. It might for some and maybe not for others. But here, it will work for any polynomial. So let f be a polynomial function and a be a real number. Then if you take the limit as x approaches a of that polynomial function, that's the same as if you just took the a that you're trying to approach and just plugged it into your function. This is one of the most useful properties that we have of limits, because polynomials are one of the most common types of function. So let's take a look at some examples of this. Let's say we want to take the limit as x approaches 2 of the number 5. Well, that's just a constant. And we saw before that when you take the limit of a constant, it just stays the constant. Okay, so that's going to equal to 5. Right? Let's take the limit as x approaches 2 of x. Okay, well, we saw before, this is one of our other ones. When you take the limit of x, that's just going to be whatever this number is. Okay, so the limit as x approaches 2 of x is just going to be whatever this number is. In this case, it's going to be 2. Now let's step it up to a big polynomial. We're going to take the limit as x approaches 2 of 2x squared plus 6x minus 5. Now here what I'm going to do is I'm going to do this two different ways. The first way is the long way. I'm not suggesting you do it this way. I'm saying this would be the long way to do it using all of these properties. But then I'm going to do it the short way by using this final property. So the long way would be like this. I would say, well, look, I'm adding and subtracting things. And I know that I can separate that as the limit of each of these with a plus or a minus. In other words, this is going to equal to the limit as x approaches 2 of 2x squared plus the limit as x approaches 2 of 6x minus the limit as x approaches 2 of the number 5. Right? That's linearity. Anytime I have a plus or a minus in between the functions that I'm taking the limit of, I can just take the limit of each piece and then stick the plus or the minus in between. All right, so right here, instead of adding and subtracting and then taking the limit, I can take the limit of each piece and then stick the appropriate plus or minus in between. Notice that the other part of linearity, though, tells me that if I have a constant right here, I can always pull that out. That's the other part of linearity. If I have a constant right here that I'm taking the limit of a constant times a function, I just pull the constant out and say, okay, take the limit of the other part and then multiply by c at the end. So right here, that's equal to, I can pull the 2 out, so that's going to be double the limit as x approaches 2 of x squared plus 6 times the limit as x approaches 2 of x minus the limit as x approaches 2 of the number 5. Finally, right here, I notice I have a power on this. Oh, but that's one of my other properties. That was not linearity. That was not linearity. That's only these two. But I have one property down here that says as long as I have a integer, so as long as I have a counting number as my power right here, I can either take the power first and then take the limit, or I can take the limit first and then do the power at the end. Okay, so I think that's what I do here. Let me just take the limit of x and then square at the end. So that's going to be 2 times the limit as x approaches 2 of x, and then that whole thing gets squared, plus 6 times the limit as x approaches 2 of x, minus the limit as x approaches 2 of 5. But now each of these I can do because of the two properties I had before. The limit as x approaches 2 of x, that's just 2. So that's going to be 2 times that whole thing. We already know from before, that's the number 2. Squared plus 6 times, and then same thing right here, that's the number 2. And then if you take the limit of a constant, well, it's just going to stay that constant. Okay, so that's going to be 2 squared is 4. 4 times 2 is 8. Here, 6 times 2 is 12. So you have 8 plus 12, that's 20, minus 5 is 15. So that's the long way to do this. And this would be using all of the properties that we saw over here. Mostly these two properties here, along with linearity, and we ended up using this second to last one down here. But because all of those properties are true, we can show that for any polynomial, basically, to take the limit, you just plug that number into the limit. You just plug the number into the function, I mean. So here the other way to do this would be to simply say I'm going to take the limit as x approaches 2 of 2x squared plus 6x minus 5. And that would be, well, just plug a 2, I hear that 2 right there, in for all of your x's. So that's going to be 2 times 2 squared plus 6 times 2 minus 5, which if you notice is exactly the result we got here after those first 3 steps. 2 times 2 squared plus 6 times 2 minus 5, which of course will give us 8 plus 12 is 20 minus 5, the exact same answer of 15. So the properties that we see before are nice because they apply to a great deal of functions. Here, notice, no one said these are polynomials. This will apply to trigonometric functions, sine, cosine, tangent. This will apply to logarithms, exponentials. It will apply to hyperbolic functions. You say, I'm not familiar with hyperbolic functions. You will be in calculus. Hyperbolic functions are introduced there. These apply to rational and radical functions as well. All of these properties apply to any function. However, by using these in tandem with these first 2 simple properties, we learn an extremely useful property. And while it applies only to polynomials, polynomials are an important enough function that it is going to be a useful property to have through calculus. All right? So go ahead and give this a try. You don't have to do it the long way. In fact, I would discourage you from using the long way. I would encourage you to use this shorter property. Go ahead and find the limit as x approaches 3 of 4x squared minus 6x plus 7. Go ahead and pause the video, give yourself the time you need, and once you're done, unpause and we go through it together. All right. The property essentially says, take that number 3 that you're trying to approach and plug it in. So that's going to be 4 times 3 squared minus 6 times 3 plus 7. That's 9 times 4 is 36 minus 6 times 3 is 18 plus your 7. Okay, so here we have what? 36 minus 18, that's going to be 18, plus 7 will give us 25. So there we go. The limit as x approaches 3 of this polynomial is the same as what you get when you take 3 and plug it into that polynomial. And that gives you 25. Now, that works wonderfully for a polynomial. But what if you don't have a polynomial? Can you just plug in the number? Well, sometimes. Depends. Well, that's the end of our section, right? No. It depends. And how can you find out whether or not it's that simple? Well, you can try it. Basically, try to plug in the number, and if it works, great. If it doesn't work, well, then there are other things you need to worry about. You say, well, what do you mean if it doesn't work? Well, let's take a look at some examples. Let's go ahead and try to find the following limits. We're going to go ahead and find the limit as x approaches 5 of x squared minus 5 over x plus 5. Okay? Now, we have properties that apply to polynomials. However, this first list of properties right here, this big list of properties, this doesn't require any specific kind of function. It just says a function. Okay, so we can try these with any kind of function. Now, it doesn't mean we're going to be successful, but we can try it. All right, so let's take the limit as x approaches a of f of x over g of x. So after all, that's what we have right here. We have the limit of a fraction. Okay, well, that's going to be the limit of the top divided by the limit of the bottom. So let's give that a try. That equals to the limit as x approaches 5 of the top over the limit as x approaches 5 of the bottom. And notice that the top and the bottom are polynomials, which means now we can use our simple property of just plugging in the number. Okay, well, let's see what happens when we plug in the number. If we plug in 5, 5 squared is 25. 25 minus 5 is just 20. Okay, that's good. What if I plug in 5 here? Well, that'll be 5 plus 5 is 10. And 20 divided by 10 is 2. Okay, so here it is acceptable to plug in the number. And you say, well, how do you know? Because you got an answer. Essentially, if it's not okay to plug in the number, it's not because you got the wrong answer. It's because you don't get an answer. Here, we got an answer. For any nice, well-behaved function that we're going to deal with, polynomials, or fractions made up of polynomials, or square roots of polynomials, things like that, we're basically going to give it a try. And if you get a number, well, then you got a number. That's it. That's your answer. Well, then you wonder, well, what does it look like if you don't get an answer? How does that even work? Well, we've seen examples like this previously. Let's say we're looking to find the limit as x approaches 5 of x squared minus 5. Oh, sorry, x squared minus 25 over x minus 5. All right, well, we could try using the same property. We could take the limit of the top and the limit of the bottom. And when you do that, of course, that works because it's just a fraction. So you're left with the limit of x squared minus 25 over the limit of x minus 5. Okay, so now we can use our nice property, which tells us plug in the number. Okay, 5 squared is 25. 25 minus 25 is 0. Over. You plug in 5 right here. 5 minus 5 is 0. And that's gibberish. That's nonsense. This is undefined. So you're saying, oh, so that means I don't have a limit, right? I don't get an answer. Well, no. It doesn't mean you don't get an answer. It just means you can't get an answer this way. Basically, if you can plug in the number and get a number, great, you're done. But if you plug in the number and get something undefined, you're not done. You have to find some other way to do it. Okay, so how do you do that? Like, how can I take this limit if I don't have the ability to just plug in the numbers? Well, one way to do it, of course, is you can build a table. You can say, okay, plug in numbers close to 5. 4, 4.5, 4.9, 4.99, 6, 5.5, 5.1, 5.001, and that will help you find what your limit approaches. Oh, but there is another way, because after all, we have algebra under our belt. We've taken plenty of algebra classes, which means that we know how to simplify algebraic expressions. If this can be simplified in such a way that you can plug in the number, then you'll be able to get a result. So right here, I notice that my numerator can be factored. So right here, I'm going to go ahead and cross this stuff out because this is gibberish. It gives you something that's nonsense. 0 over 0 is undefined. In fact, it's nonsense. So that's not going to work. But I notice here that this can be factored. So let me go and do this off to the side. If I have x squared minus 25 over x minus 5, that's the same as x plus 5 times x minus 5 over x minus 5. Oh, but look, these two are common factors. I say that as if I'm surprised, right? These are common factors, which means they divide away. So what that means is that x squared minus 25 over x minus 5 is the same as x plus 5. But now the more attentive of you will say, well, no, that's not quite true. For those of you who remember your algebra very well, you remember that's not quite true. Because here, you can't divide these if they're both 0, because you'll run into the same problem that you had over here. If both of these are 0, then you can't cancel them, because it's undefined to say 0 over 0. Oh, but how does this ever end up being 0? How do I get both of these to be 0? Oh, well, you would plug in number 5. Okay, so that means that here, these are equal to each other as long as these aren't 0. Or in other words, these are equal to each other as long as x is not equal to 5. So for the more attentive of you, you may have picked up on that. These are not equal. They're usually equal except at one point. These are equal except when x is equal to 5. But see, that's the beauty of the limit. You're never actually going to need to plug in 5, because we tried that. We tried plugging in 5, and it was nonsense. So what we're going to do is we're going to plug in numbers that are very close to 5. And the thing about numbers that are very close to 5, they're not the number 5. So here, these are not always equal, but the one time when they're not equal is the one time we're never going to do. That's the one value of x we're never going to use. So this can be exchanged for this one without having to worry. Oh, but guess what? That's the limit of a polynomial. There is no more rational expression. There is no more dividing by 0 or anything else, really. And now I can just plug in the number. 5 plus 5 is 10. And that's my result. So can you plug in the number? The answer is sometimes. Now, if it's a polynomial, you can always plug in the number. If it's not, give it a try. You might just get a number, and that's it, you're done. But if you don't, if you get something undefined, 0 over 0, then you're going to need to find some other way to do it. A common way of doing it is by simplifying this expression by factoring and simplifying. Note that this is not always equal, but the time it's not equal is the one case that we're never going to worry about. All right? The one time when this is not true is when x is equal to 5. But 5 is the one number we're never going to plug in. We're going to plug in 4 and 4.9 and 5.2 and never 5. So this is perfectly valid. Let's see one more of those where plugging in the number just doesn't work. We're going to take the limit as, let's say, x approaches 0 of the square root of 16 plus x. And then we're going to have a minus 4, and that's going to be on the outside of the square root, over x. Okay. You should always try to plug in the number. Because, yeah, there's going to be plenty of times where that doesn't work. But if it does work, well, then you're done. All right, let's see what happens if we plug in 0 here. Well, the denominator will be 0, and right away, that's it. That's not going to work, is it? Because dividing by 0 is nonsense. Okay, so obviously plugging in 0 is not going to work. Notice if you plug it in on top, that's also going to give you 0. 0 plus 16, that's 16. Positive square root of 16 is 4, minus 4 is 0. So this turns out to be exactly the same as the previous one, 0 over 0. Okay, so obviously I cannot just plug in the number, because if I do plug in the number, I get 0 over 0, which is not an answer. It's nonsense. It's not right or wrong. It's gibberish. Okay, so here, what do I do? Well, one technique that you can use is factoring. But by looking at this one, I think factoring is kind of off the table. You might be able to factor that, but nothing's coming to mind. Nothing useful is coming to mind for factoring. Well, there's another technique that is going to take advantage of a property of binomials. Here, we have the square root of something minus something. Now, technically, I guess this is also the square root, right? It's the square root of 16, but whatever. You have at least one square root. And here, that's either plus or minus, right, those square roots. We're going to use a technique called rationalizing. Now, up until now, the only time you've ever seen any kind of rationalizing is rationalizing something so that you don't have a square root in a fraction. Up to now, the only time you've seen rationalizing is like in trigonometry, where you end up with an answer that looks like this, 1 over square root of 2. And what you do is you multiply by the square root of 2 on the top and bottom, and that gives you a square root of 2 on top and then square root of 4, which is just the number 2, on the bottom. And this is called rationalizing the denominator. And that's the only time you've really ever seen rationalizing. It's called rationalizing because you're taking something that's irrational and turning it into something that's rational. You're rationalizing it, turning it into a rational. Okay, so right here, if this square root wasn't there, it'd be a lot nicer, right? Because square roots make things more complicated. And also square roots, this wouldn't be 4 minus 4. It would be 16 minus 4, right? Which wouldn't be 0. You say, well, but the bottom would still be 0. Well, yeah, but maybe in the process of changing the top, the bottom will also change. Okay? So we're going to try that. It's called rationalizing. Now you might notice that there is no square root in your denominator. Okay, well you don't always have to rationalize the denominator. The technique that we're going to use is rationalizing. Whenever you have a fraction that gives you an undefined expression when you plug in the number, one technique is to rationalize wherever the square root is. So if there's a square root on the bottom, try rationalizing the bottom. On the other hand, if the square root's on top, try rationalizing the top. The way you're going to rationalize it is by multiplying whichever one has the square root by its conjugate. Like this. The conjugate, same term, opposite sign. That's what conjugates are, yeah? Whatever you do on the bottom, you're going to do on top. Whatever you do on top, you do on the bottom. So I'm going to multiply the top and the bottom by the same amount. Okay. So this is now the limit as x approaches 0 of, all right, let's start multiplying. If I multiply these two together, that's the square root of 16 plus x times the square root of 16 plus x, something times itself. That's the square root of 16 plus x squared. Oh, the square root squared. That's going to cancel out the square root, and you're just going to be left with 16 plus x. If I multiply this one times this one, 4 times that square root. Okay, that's plus 4 times the square root. But then right here, this one's going to be minus 4 times the square root. And those will add up to give me 0. Finally, the last expression is negative 4 times 4 is negative 16. Whenever you rationalize something to try to evaluate a limit, the one that had the radical expression, go ahead and multiply all that out and simplify. The one that didn't, go ahead and leave it without multiplying it out. There's a reason for that, which we'll see in the next step. All right. So I've gone ahead and multiplied. The denominator, I'm going to leave it the way it is. I'm not actually going to distribute it. But the numerator, I see there's things that I can simplify. 4 root 16 plus x minus 4 root 16 plus x. Those are going to add up to 0. And right here, I have 16 minus 16, which again is equal to 0. So what's left? Well, all my terms are gone except for an x. So that's going to give me the limit as x approaches 0 of x over x times the square root of 16 plus x. And then outside of the square root, we have a plus 4. But notice here, we have the exact same situation that we had before. I have a factor on top and a factor on the bottom. I can cancel. I can divide them. Again, the more attentive of you will say, no, you can't. Those are not always equal, right? Well, when is this not going to be valid? When can I not divide? Oh, when they're both equal to 0, because again, I end up with that problem right there. Oh, but the only time they're both 0 is if I plug in x is equal to 0. And because I'm taking the limit as x goes to 0, 0 is the one number I will never plug in. So here, I can't divide these out if x is equal to 0. But here, x will never be 0. So I can divide those away. X divides x to give us 1. And so now we're left with the limit as x approaches 0 of 1 over the square root of 16 plus x plus 4. Notice we don't have our answer yet, and in fact it looks very similar to what we had before. We have a radical over a polynomial. Over here we have a polynomial over a radical. But now, look what happens when you plug in. Your top is not 0, is it? It's a constant, 1 in this case. What about the bottom? Well, let's see. let me write it out here. The limit as x approaches 0 of the top over the limit as x approaches 0 of the bottom. Okay. Oh, well, that's a constant. And we've seen the property before that if you take the limit of a constant, that's just that same constant. So that's going to equal to 1 on top. And if you take the limit of a sum, okay, you can take the limit of each one separately. So in other words, here, that's going to be 16 plus 0. That's going to be 16. Square root of that, because after all, we can take the square root after we've taken the limit. That's fine. That's one of our properties. So that's going to give us 4. And then that's a constant, so its limit is going to stay 4. So when you take the limit, that's going to be 4 plus 4, which gives us the denominator of 8. And now we don't have gibberish. Now we don't have 0 over 0 like we would have if we plugged in 0 at the beginning. Now we have a result of 1/8. And you can check that. If you actually go through and pick numbers close to 0, if you pick 1 and then a half, a quarter, an eighth, a 16th, and then try with negative numbers, try -1, -1/2, -1/4, you will notice that as your x value gets closer to 0, your y values will get closer and closer to 1/8. Well, I mean, it will, you'll probably do it with a decimal, so they'll get closer and closer to 0.125. But either way, you'll get closer and closer to this. So even if you're using a table to find those values, you're still going to get that same result. So go ahead and give this a try. Let's have you try a few of these. I'm going to give you some. You're not going to be able to plug in the number. All right. I mean, you can try it, but I'm going to give you some where you can't just plug in the number. But you can still do it by factoring and simplifying. Or if there's a radical, you can do it by rationalizing and then simplifying. All right, so go ahead and give this a try. We're going to have you find the limit as x approaches 3 of x squared minus x minus 6 over x squared minus 9. Okay. And then for your other one, go ahead and try go ahead and find the limit as x approaches 9 of the square root of x minus 3. Notice the minus 3 is on the outside, not inside the square root, divided by x minus 9. Notice if you plug in 9 here, you're going to get 0 over 0. Try to plug in 3 over here, it's going to give you 0 over 0. But you don't need to plug in the number right away. Go ahead and give that a try. Pause the video, give yourself the time you need, simplify as much as necessary, and evaluate the limit. Once you have your results, go ahead and unpause, and we'll go through that together. All right, so let's take a look here. This first one, polynomial over a polynomial. We're going to factor. Okay. Let me go ahead and do this over here to the side. If I have x squared minus x minus 6 over x squared minus 9, that's going to equal to, I can factor this one. X squared means these are going to have two factors, both starting with an x. Two numbers that multiply to give me -6 and add up to give me -1. Those are going to be -3 and +2. So I'm going to have a -3 and a +2 to complete my factorization. X minus 3 and x plus 2 factors the top. On the other hand, the bottom is a difference of squares. So x squared minus 9, you square an x to get the first term, then you square a 3 to get the second term. So that means that this factors as x plus 3 and x minus 3. And right here, these two divide away. And that's true. This is equal to this. X squared minus x minus 6 over x squared minus 9 is in fact equal to x plus 2 over x plus 3 for all numbers except 3. Right? Because if you have x equals to 3, that would be 0 over 0, which you can't divide. You're running into the same problem you had over here. That's undefined. Okay, so this is equal to this except when x is equal to 3, because that's when that divided expression would have been 0 over 0. Oh, that's fine, because I'm never going to plug in 3. I'm going to plug in 2.5 and 2.9 and 2.99, but never 3. So here I can just exchange this expression for this expression without ever having to worry about the one exception. So that's going to be the limit as x approaches 3 of x plus 2 over x plus 3. Oh, but now it's perfectly fine. I can plug into those. Here that's going to be the limit as x approaches 3 of the top over the limit as x approaches 3 of the bottom. And since those are both polynomials, I can just plug in the number. 3 plus 2 is 5. 3 plus 3 is 6. And there's my result. If you tried to plug in 3 at the beginning, you would get gibberish. You would get 0 over 0. But if you factor and simplify, you're going to end up being able to plug in here after this simplification, giving you 5 over 6 as your result. For this one, we're going to do something similar. We're going to simplify. Note that this one doesn't factor out the same way the previous one does. So we're going to rationalize. Now, I said something, and I'm going to correct myself slightly. I said this doesn't factor. It actually does. In a way that you're probably not used to seeing. You say, how on earth do you factor this? That's linear, so it doesn't factor anymore. And this is got a square root. So yeah, there's no way that factors. It does, because the bottom is the difference of squares. You say, no, it's not. I mean, okay, 9's a square, but that's not a square. Yes, it is. It's the square of the square root of x. That's one of those little secrets that no one really ever talks about, right? When we say the difference of squares, we don't mean it has a square. We mean it's the square of something. And even a linear expression is the square of something. It's the square of its own square root. So right here, I'm going to go through and I'm going to do it by rationalizing. But I would also like to show you another method to do this, because this is one of those things that doesn't come in handy very often, but it comes in handy often enough that it's worth seeing. So let me go ahead and, I will come back and I'll do this one with rationalization. But first what I want to do is I want to do this. I'm going to say, okay, x minus 9. I'm going to think of x minus 9 as the square root of x squared minus 3 squared. That's x minus 3. But if I write it this way, it's the difference of 2 squares. So whenever I factor the difference of 2 squares, just like I did over here, what did I square to get the first one? That goes first. What do I square to get the second one? That goes last. One's got a plus, one's got a minus. So this would be the square root of x plus my 3, and that will be the square root of x minus my 3. Isn't that weird? It works though. Multiply it. That's x plus 3 root x minus 3 root x. Those add up to 0. And 3 times negative 1 is negative 9. 3 times negative 3 is negative 9. Multiply those out. That does give you x minus 9. Okay. Now, there is one little word of warning here. Keep in mind, if you plug in a negative, these become imaginary numbers. And, well, we haven't talked at all about imaginary numbers here. Oh, but notice that the numbers you're plugging in are numbers close to 9. And, well, negative numbers are not close to 9. Numbers that are close to 9 are like 8.9 and 9.2. So here, yeah, it's true. If you plug in a negative number in for these x values, that is going to be an imaginary number, which we haven't really talked about how to work with those. But it's irrelevant, because here, the numbers you're going to plug in will not cause that to happen. Okay, so if I take the square root of x minus 3 over x minus 9, that's the same as the square root of x minus 3 over the square root of x plus 3 times the square root of x minus 3. And now, hey, look, these divide away. Well, they divide as long as you don't have the number 9 plugged in. Because if you plug in the number 9, Square root of 9 is 3, minus 3 is 0 over 0. Okay, so here these divide away as long as x is not equal to 9. But again, you're not plugging in 9. You're plugging in numbers close to 9. 8.7, 8.8, 8.9, 8.99, but never the number 9. So here, this is equal to 1 over the square root of x plus 3, except when x is equal to 9, which, again, we don't need to worry about. So here that can be written as the limit as x approaches 9 of 1 over the square root of 9 plus, the square root of x plus 3, which now we can take the limit of the top and the limit of the bottom separately. Limit as x approaches 9 of 1 over the limit as x approaches 9 of the square root of x. And then outside the square root I have a plus 3. Oh, but the limit of a constant is 1. And here I can plug in that 9. 9, take the square root is 3, plus 3 is 6. And there we go. Now, if you are not familiar with this kind of factorization, if you have never seen something like this before, I wouldn't worry about it. It's not a standard kind of practice that we do. It's not something we see used much, in particular because it does introduce imaginary numbers in certain situations. However, as long as you're careful and make sure you didn't accidentally introduce any numbers that you're not prepared to deal with, this actually works out quite well. You get 1/6. But since this problem, I suspect you probably did it with this technique where we rationalize our square root to make it go away, let me do this problem one more time using that technique. So same problem, but with the other technique. Find the limit as x approaches 9 of root of x minus 3 over x minus 9. So the rationalization technique for this one is I'm trying to make the square root go away from the top, so I'm going to multiply by the conjugate of the top. Whatever I do on top, I do on the bottom. Okay. All right, so that's going to give me the limit as x approaches 9. Square root of x times square root of x, that's going to be just x. Square root of x times 3, that's going to be 3 root x. And then negative 3 times root x, that's minus 3 root x. And then negative 3 times 3 is negative 9. Now, the place where the square root is, we're actually distributing that out. The place where it didn't have a square root to begin with, we're going to leave that the way it is. And the reason we leave that the way it is because if you distribute it, you're just going to have to factor it back out at the end in order for the proper expressions to divide. So it's not wrong to multiply it out, but it's unnecessary and takes up extra time that doesn't need to be happening. Here, these two will subtract away. 3 root x minus 3 root x, that adds up to 0. So we're left with the limit as x approaches 9 of x minus 9 over x minus 9. And now you see why we didn't distribute, because that one exactly as it is what's going to divide that expression on the top, times root x plus 3. And now, as long as you don't, that should be a minus. X minus 9. There you go. So now, as long as you're not plugging in the number 9, which you're not, you're plugging in numbers close to 9, as long as you're not actually plugging in the number 9, these two divide away. Now, if you do plug in the number 9, that's 0 over 0, which is undefined. But we're not going to plug in the number 9. So that's okay. We can divide those away. So that's going to give us the limit as x approaches 9 of 1 over, these two have divided away, just the square root of x plus 3 on the outside of the square root. which means we can now take the limit of the top, limit as x approaches 9 of 1, over the limit as x approaches 9 of the square root of x, and then on the outside of the square root we have a plus 3. Or in the numerator, that's the limit of a constant, which will stay constant. And in the bottom, that's going to be the square root of 9, which is 3, plus 3, for a result of 1/6, which if you notice is exactly the same result that we see here. So even if you change the technique, even if you change the way that you evaluate the limit, the answer shouldn't change. Just because you've changed how you arrive at the answer, note that your answer is still the same. So that's it. That brings us to the end of this section and the end of this topic. Note that this is not a complete development of the properties. In particular, there's no proof for any of them. And there have been some details that have been glossed over. This is a pre-calculus course. In a calculus course, you'll have a bit more detail. You'll have full definitions and proofs of these theorems. But for now, this is a good introduction to them, as well as showing you a few basic tricks that will come in very handy in calculus. All right? So that is it for this section. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I hope everyone has a nice day.